Three research groups jointly created a crystal made of electrons, confirming a prediction first made in 1934. In the history of scientific research, there have been cases where two scientists arrived at the same conclusion despite being completely unaware of each other's work. In the summer of 2021, a rare event occurred once again, but this time, thanks to the power of global connectivity, the entire world witnessed it together. Three different groups were able to compare the results and quickly reach a common conclusion. Three different research teams all attempted to create crystals from charged electron particles, and one of them succeeded, quite by accident. The breakthrough occurred when researchers discovered how to apply a semiconductor layer, just one atom thick and cooled to near absolute zero. A research team led by two Harvard University scientists, Hong Kong Park and Eugene Demler, discovered that when a certain amount of electrons exist in a semiconductor device, they stop moving in a puzzling manner. Noticing the similarity between this phenomenon and the Widner crystal, a concept so far only proposed in theory. Physicist Eugene Widner discovered this, prompting the research team to delve deeper into the strange phenomenon. According to ancient documents, Professor Widner suggests that under the influence of electric forces, electrons arrange themselves into a thin layer and form a network with triangular meshes. The arduous journey of Park and Demler's research team was not a solitary one. A team of theoretical physicists, led by Eugene Demler from Harvard University. We have developed a theory regarding the effects observed when examining the excitation frequency of the acetone state, and these results perfectly match the experimental observations. Etta Imamoglu, a researcher at ETH, said, Imamoglu presents research findings on acetone, specifically the bound state between an electron and an electron hole. The state of electron deficiency at a point refers to the concept where an atom or a crystal structure composed of multiple atoms can exist in a state of electron deficiency. Imamoglu's research team also applied the technique outlined in the document on the Widner crystal growth method. Based on the property of repelling other particles, it can be seen that electrons behave like magnetic poles. In a solid object, electrons can contribute to forming periodic crystal structures. However, the situation completely changes when electrons exist in a liquid environment. Because the electrons in the liquid are highly responsive, they can change states even under the slightest influences. To keep electrons in a stable state, the conditions acting upon them must reach absolute precision. First, having fewer electrons will make the experiment a bit easier. In that case, when there is a certain amount of electrons, scientists can easily arrange them into a complete lattice structure. Additionally, there is a third group specializing in the study of semiconductors that are just one atom thick. Author Fan Kuang from UC Berkeley also attended the event. The research team also experimented with arranging electrons into a crystalline structure. The distance between the electrons in this study is greater than in the two previous studies. Additionally, the temperature factor must also be considered. When the temperature drops to a low level, the movement of particles gradually slows down and eventually stops completely. As the temperature approaches absolute zero, the electrons will cease their chaotic motion. Will remain nearly unchanged from the previously determined position. This is when quantum effects become prominent, replacing behaviors that were once the domain of classical mechanics. Even in a water environment, electrons still fully exhibit their particle properties. When the temperature is low enough, electrons can be easily held in place. When there are enough electrons, they will automatically arrange themselves in an orderly manner. Electron is a fundamental charged particle in nature. From this, we can deduce that a group of electrons will form an electrical power source. However, the concept of Widner crystals reveals a completely different reality. Electricity is generated by the movement of electrons, not by their mere existence. When the electrons fit perfectly within the crystal lattice structure, they will have less room to operate and generate electricity. This is precisely why scientists claim they have successfully created a crystal made of electrons. Almost motionless in place, the electron structure does not function properly as a semiconductor. Instead, it exhibits insulating properties. Quantum fluctuations occur as the temperature approaches absolute zero. This phenomenon has caused a quantum state transition. to transform a freely flowing solution into a quantum crystal, also known as a Wigner crystal. Scientists believe this quantum state transfer could become a reality, plays a key role in many future quantum systems. When the Harvard research team realized they were holding Wigner crystals in their hands, they experimented with quantum melting, dissolving the structure at a non-classical phenomenological scale. The entire system is watching to see what happens. All activities mentioned in the research reports all occur on such a small scale that no optical microscope can observe them. The STN microscope is a specialized device for observing atomic-scale objects. You messed up the crystal structure again. Mr. Wang's research team can observe with the utmost precision and detail. When placing a single atom-thick layer of graphene on top of the crystal structure, the Wigner crystal has a minor influence on the electron structure of the raphine layer, sufficient for the STN microscope to observe the internal structure. To prove that they had indeed created Wigner crystals, the research team used photon particles to bombard and eject electron particles, producing acetone that can be